So when I say N plus L, or when anybody says N plus L, they're talking about like SP, okay? And for instance, SP, sorry. They're talking, for instance, like 1S subshell, 2S, 2P, 3S, 3P, 3D. And each one of those subshells has an N value, which is the number, and has an L value. And I've been telling you guys you need to cross-reference your L value from what you remember as S. It's really L is equal to 0. From what you remember as P, it's L is equal to 1. D, L is equal to 2. F, L is equal to 3. So that's what we mean by the lowest N plus L rule. And then we started on Wednesday finding homes for electrons. So those blue lines are electrons, and you recognize those little boxes as orbitals. And so given the atomic number of an element, that's how many homes you need to find electrons for. Okay, and then we got to carbon, and we said with carbon, we now run into a situation where we have 2 electrons after the 2s, and there are 3 degenerate orbitals in this 2p subshell. Okay, 3 orbitals that are the same energy. So this is where they're going to spread out. And that pattern's going to continue with nitrogen, okay, and then oxygen we're going to kind of revisit and buddy up just like you would kids in sharing a room in a house. Okay, and neon has that complete octet down there at the bottom. The 2s2, 2p6, okay, is an octet. So that was box and arrow notation, otherwise known as orbital diagrams. I think this textbook uses orbital diagrams for box and arrow. And this is another way to say how electrons are configured, but this, you don't have to draw the boxes, so this is a lot easier. Where the little superscript now means the number of electrons in that subshell. All right. So now this is where I think we are ready for the arrow diagram. So I'm going to show you, before I show you the arrow diagram, this is what I would do for my intro Gen Chem students, so why not do it for y'all, right? Sometimes drawing the arrow diagram, doodling it, can help you on a test. And you're going to recognize, okay, 1s subshell. And we line up the S's and we line up the P's. And of course those numbers correspond to N values. I better not do too much talking or I'm going to mess up. Energy level N is equal to 4. Now we get an F-type subshell. And honestly, I'm not going to do any more beyond F. Okay, we don't need them as we're accommodating electrons in their ground state, even up to the most complicated atom we have. So I'm going to do energy level N is equal to 5, 5s, 5p, 5d, 5f. Okay, I'm going to do all the way up to 7. In Chem 122, my introduction to general chemistry, actually students get points for drawing this on an exam. So those are just subshells, and then the arrow part of the arrow diagram, of course, looks like this. Oh, go back. Oh, did it really do that? Oh well, that's the biggest part I wanted to show you. Maybe it'll... Okay. Okay, so now on to the real slide. Notice these are grayed out because a minute ago when I did it, I was like, we don't have any as long as the electrons are in their ground state. We aren't finding homes in these, all right? So here's the arrows. And as we draw the arrows through subshells, all of the subshells that the arrow goes through have the same N plus L value. N plus L value of 1s is what? 1 plus 0 is 1. N plus L value of 2s is 2 plus 0 is 2. Actually, both 2p and 3s have an N plus L value of 3. Okay, 4, 5, 6, 7, 8, 9, and 10. Okay. So notice that in the arrow diagram, they are directional. So when this in this little box up here, it says fill in the direction of the arrows, so it's always going to start kind of upper right and go down. Upper right and go down. All right. So another way of looking at an arrow diagram is this. It's very similar. Okay, it just kind of doesn't have the bottom. But that's okay. So let's go ahead and use the arrow diagram to write out some electron configurations for electrons around some neutral atoms. We'll pick on potassium first. Potassium's atomic number 19. So for 19 protons, we must have to have 9 homes for 19 electrons if it's neutral. So the way this works is I have builds that basically circle where it goes. Oh, and by the way, we are not going to use the box and arrow notation. No hand cramp right now. We're going to use the spectroscopic notation. So you'll hear me say 1s, a little bit of pause, 1s2. I guess the pause is between the subshells. So the last number I say is the number of electrons in that subshell. Then we go on to the next diagonal, 2s2. I feel like I'm playing bingo calling out numbers. Then we're ready for the third diagonal. We're going to start at the top of the third diagonal. So we're going to go 2p, and we follow the rules we know about p-type subshells, and they can accommodate 6 electrons. Okay? And notice we're only up to 4, so definitely we're going to go ahead and fill that. So it's 2p6. And anytime you hit a generic S2P6, we call it NS2, NP6, you have reached a rare gas. Okay, so this is, what, 10 electrons if we add up the superscripts? If we look on the periodic table, we see that actually corresponds to the rare gas neon. But we're not done yet. We need homes for 9 more. So you can see on the arrow diagram, we're going to go 3s2. And then we're going to go to the fourth diagonal. The top of the fourth diagonal is 3p6. So we got to be careful. And actually, by going 3p6, we have not gone past our 19. We have 10 plus 8. We have 18. So the other thing, though, is we have reached another rare gas. So that actually corresponds to, on the periodic table, underneath neon, that's argon. So we have 18, we need homes for 19, 1 more, and we know where it's going to go. We're going to continue on that diagonal, so it's 4s1. This is a good example to show, because especially, you guys have been exposed to this before, but especially my students who have not had chemistry before, they want to throw in the 3D, and that ain't how it works. That's not how it works. 3D, you cannot. And the reason is 3D has a higher n plus L value. Okay? So we're done. And you might be wondering, can I use an abbreviated rare gas notation? Yes, you can. So these are rare gases. These are rare gases, inert gases, noble gases. They're all the same thing. You can use an abbreviated notation. That works just fine. I'll go ahead and tell you what that is for this one. Looks like I'm going to wait for the next example to show you. But the abbreviated rare gas notation basically takes everything up to, let me change the color of my thing. It cuts off at the last rare gas. So what you do is you write in brackets the rare gas, the symbol for the rare gas, and then beyond that you write what the electrons are. So it's 4s1. Okay, so actually this would be awesome too. They're both cool.
So you don't have to write the first one, you just write the last one.
Yep.
So would you expect to see piggyback on that answer for the next slide?
I think so. You're wondering, because next, instead of 19, what the next one is 40. Yeah, you could pick up from there. And so kind of along those lines, let's go ahead and kind of do the first few quickly. How's that? Is that kind of what you were saying?
Well, I was wondering if we could write the
Argon.
application of argon and then start with 4s1 and then work your way up from there. And just skipping the 1s2 to s2 where you started.
Well, the thing about kind of using the rare gas notation is you always use the rare gas in the period before it. And actually, I have it on a slide. So for zirconium, sometimes I mispronounce that. Okay, so for zirconium, it's right here. So actually, instead of argon, So this is period 5. We're going to be talking more about periods. So at period 4, instead of argon, actually, it's going to be krypton in brackets. So,
Okay.
but I think you're on the right track. So 1 electron past, what did we just do? Potassium. 1 electron past, plus potassium looks like this. And so those are 20 electrons on our way to 40. So now, finally, this is so exciting, I think, because now we get to start to put electrons in a D-type subshell, specifically 3D. And D-types, we know, have 5 boxes. And if we completely fill those 5 boxes, we've got 10 electrons. So let's see, 18 plus 2 is 20, plus 10 is 30. Yeah, let's go for it. Okay, so it's kind of a check. So we need homes for 10 more electrons, because we're at 30 there. Next on the list is 4p, and we can accommodate only 6 electrons, and we need home for 10, so let's go for it. Right? So 4p6, we're going to completely fill it. Now we have arrived again at an S2p6. It's just a 4s2, 4p6. Check out the 4 though. If I go back over here to this periodic table, 4 is actually what we were just talking about. So we have arrived at krypton. I always think of Superman. Like, oh my gosh. Does that make sense? If you add up the little superscripts, you got 36 electrons. Now we better crank her down a little bit because we only need 4 more. But notice that the next stop is a place that accommodates 2, so 5s2. Okay. And then this is, to me, and as many years as I've been teaching this, I like the arrow diagram because this is, to me, I can clearly see where my last 2 electrons go. They go in the 4D. 4D2, and we're done. Stop. Fine. There's another way I'm going to show you how to come up with electron configurations, and it's just looking at the periodic table. And I usually tell students that the arrow diagram will always get you there. The periodic table, not so much. Okay, so this is right. Now we're going to talk a little bit about scrambling scrambling our electron configuration. This is our electron configuration. This is in the order of filling. Okay. There is an advantage to putting it, what we say, in the order of increasing n. So as I write this down, let me kind of emphasize what got scrambled. When we say n, we're talking about the number. So do you see, for instance, where this goes? This goes 3, 3, 3. But then we have 4, 4, 4, and heaven forbid we have a 5 there. So what you see with this second notation, basically, I don't know how you want to look at it, but is kind of moving this one over and moving this one over, kind of collecting our ends. However you want to think of it. But it's still the same ways of saying where electrons are hanging out. Probably it won't be until Monday when we talk about valence electrons, but I'll go ahead and show you the beauty of this. In doing this, we can really highlight where our valence electrons are. Our valence electrons are always in the highest n. And so these, specifically, these cute little 2 electrons are your valence electrons. All right, so one more thing before I leave this. So, does this work for you guys? If you were going to use the abbreviated notation for this, we'd go with what? KR, right? And then what? Yep. Does that make sense? That'd be awesome. That would do it.
Then you do it that way though? Do you have to put 2 after it, or is that only if you?
That's a good question. I've had this question before. She's like, well, do we need to go ahead and rearrange this in order of increasing n? Doesn't matter. It's optional, but you for sure need to show those 4 electrons, and that's where they are. Yeah. All right, so from 40, now we go to 53. So let's kind of accelerate the process, if that's okay with you. Clear up to basically krypton. So I'll just, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. And then we said beyond that we go to the 5s2. And then we go ahead and completely fill that D-type subshell with 10 electrons. So beyond the 5s2 we have 3d10. Just for kicks, I usually kind of do a combination of using the periodic table and the arrow diagram. But can you see where iodine is clear over here? It's almost next to the next rare gas. You're like, oh, dang it. One more electron and we'd be at xenon. Okay? So let's see, 36, 37, 38. So we have 48 here. Okay? So 48 to 53, we need 5 more electrons. All right. And next on the block, we have a p-type, which can accommodate 6, but we only need 5. Okay, so 5p5, and we're done. Is that right? One more electron. Okay. So now you're going to see, actually, this rare gas is going to be based upon the same rare gas as the one before it, right? Kr. The rare, I should say the abbreviated rare gas notation. So this is what you guys wrote down. Okay, unscrambling them. Oof. Unscrambling them. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, and it peters out with 5s. 5s2, 5p5. Whew. But see, to me, to do the abbreviated rare gas notation, I mean, you really got to do the order of filling because it makes most sense to me. Because in the order of filling, when we got to this guy right here, actually those pair, in the order of filling, we knew that we had a rare gas. And that rare gas, we said, corresponded to krypton. So, does that make sense? I think the order of filling is easier to come up with a rare gas notation. And back to what Alexa said, here, see, I've unscrambled not in the order of filling, but in the order of increasing n. But I'd take it either way. Okay? Alrighty then. So here's some kind of do's, not necessarily don'ts, about using that kind of bracket rare gas. It always has to be the one in the period before it. And it can be used with, if you're using that box and arrow notation. So sometimes students will actually at the top of the column, and I don't know if this helps them or hurts them, honestly, but they'll write, since every S-type subshell has one box, it can actually accommodate, 2 electrons. It maxes out. The P-type has 3 orbitals. Each orbital can hold 2 electrons, so it maxes out at 6 electrons. Okay, the D-type has 5 orbitals. They each hold 2, maxes out at 10 electrons. And for an F-type, if you get that far, it has 7 orbitals, each max out at 2 electrons for 14 electrons total. I don't know if that helps people, but it might. And so here, kind of as you arrive at these 6 electrons in each one of these subshells, kind of in brackets, are the rare gases you've arrived at. This one, UUO, yet to be determined. One of the things I probably need to put in a grant for it is to get updated on periodic tables. And I don't think this one's too bad. 2001, only 13 years. Sometimes I'll take like little sticky notes or something and put the new information for the new elements. So I don't know. Okay. So I mentioned that if you're trying to accommodate electrons somewhere, the arrow diagram will always get you there. There's another way to just kind of quick and dirty look at the periodic table, and you're seeing it here actually. You're seeing here how you can look at the periodic table and know how the electrons are configured. So let's go ahead and before I kind of show you the boxes, if we pick on, for instance, iodine, okay, we said that it's based upon krypton, didn't we? And then it kind of like, how do I say, it kind of goes from left to right, down a period, left to right, down a period. So after krypton, you go over to, I'm getting this period 5. So you had krypton, you had 5s2, 4d10, 5p5. Okay? So kind of what that is chunked up in is like this. The first two, and we're kind of combining something we talked about when we talked about elements. When the periodic table arranges the elements, these two columns, okay, columns are what we call groups. These first two groups, okay, I'm going to call them S block. Those first two groups are what we call S block elements. Why? Because as you're adding electrons, you are actually adding S-type electrons. Okay, and we're going to skip the transition elements for now and go over here. Okay. Over here, to finish out, these are what we call 3A through 8A. 3A, 4A, 5A, 6A, 7A, and 8A. Okay, finish out the main group elements. Those are P block. So we're adding P-type electrons. Notice that it's not just any S or any P, that the S and the P corresponds to the periods. See how that is? You could go down here to francium and radium, 7S. Okay, these would be 7P. Okay, go up 6, 6P. Does that make sense? Okay, so that's S block and P block. Here we have D block, but notice it's N minus 1. The reason it's N minus 1 is if we look and see kind of what's happening here, let's pick on, we have to pick on something here. Okay, if you look at all of these guys, notice that these elements are in the 4th period, but when we're adding D electrons, it's in the principal energy level, N is equal to 3. It's 4 minus 1, or 3. The others are covered up, but down here we're adding electrons in 6D, okay, even though that they're in period 7. Down there at the bottom, those are F block elements, those intertransition elements, the lanthanide and the actinide series. But for those, they're F blocks, so they're F-type subshells, but they are in N minus 2. So we said that the lanthanide series kind of comes out right here. Okay, so this 58 comes out right there. Okay, so it corresponds to the period 6. But look, okay, 6 minus 2 is 4. Those are 4F. And all of what I'm showing you actually is consistent with your arrow diagram. Okay, so starting here, actually, this is what we'll hit Monday. In the meantime, you are ready for, I'll just go ahead and break it out. You guys have it. I'm going to show you the problems that are at the last slide there. Okay, they look like this. You can go ahead and answer these. And some of them are like, I didn't know how to write hints for these. Like, for instance, 77 says, which of these really is correct for phosphorus? So I love the arrows. Like, oh, cool. Like, they're just, but like, for instance, doesn't this look wrong to you? Yeah. This look wrong to you? Yeah. So, I mean, you'll do fine. Follow your instincts. The next one is, which one of these is right for molybdenum? Okay. So that should be fine. Use the basic rules for electron configurations to go ahead and, my hint here, and I'm not going to write it down because there's really not much to write down. My hint there is to go ahead and draw the electron configurations and then see how they are. I know, it's mad. There it is. Okay. So what I was trying to do is I would draw, oh shoot, really? I would draw the electron configuration, for instance, as the first one, like phosphorus. I would draw the box and arrow diagram because it's asking you information about unpaired electrons. And you don't know that unless you go all the way to box and arrow. Okay, so it's going to do it again. Don't do it. Don't do it. Okay, so I need to go this way. I thought that was right. Oh, I'm already in. Okay. Okay, so I would draw a box and arrow of these guys. Sometimes you, don't want to take the time that needs to be taken to go ahead and do these. You know, box and arrow notation, then you can answer these, I think. Maybe you don't have to, but I think you have to. Okay. The next one, here's my hint for this one. Sometimes I've had students like, what the heck? But for me, the best, it talks a lot about periods. Okay, period, 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 blah, 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 blah. Okay, I would go ahead and write in, for instance, that little box up there is hydrogen. And hydrogen is in period 1, 2, 3, 4, 5, 6, 7. I would do that. Okay, this is like a little periodic table with no elements there. And what we just talked about, start to get familiar with S block, you know, P block, that's a P, not a D, D block, and of course F block would be down here. Okay? One little hint there. Which of these correspond to ground state and which are excited state? So kind of look for exceptions. Like, for instance, to me, this B right here kind of stands out. That's not right, because we said Hoone's rule says they'll have the same spin. Okay, so that must be an excited state, right? That's all right. You have to force them to buddy up, sharing rooms when there's an empty room to be had. This is your kids in your house, okay? So that must be an excited state. It's similar with this one. See, so they're not too bad, really. Easy for me to say. And then the last, almost the last two, the last four actually kind of pair up. So 85 and 86. To me, these are applying the N plus L rule. Now, I know one of the things we need to still talk about from this part are exceptions, but I want you to apply the N plus L rule. You might go ahead and come up with electron configurations, look them up in using Google, and yours don't match. But if yours are the lowest N plus L rule, you guys did great, okay? Because that's how I'm going to ask you on the test. Then the last two look like this. And I was looking at these at my office. I'm like, this shouldn't be too bad. You're supposed to say, name the element. And I'm like, these look pretty easy. You know what I'm saying? Yeah. So they're not too bad. There's no tricks there that I know of. Okay. That's it. So those are due Monday.
Mrs. Stein, when you get time, can you put up the Chapter 8 solution?
I can. Yes. I have them hard copy here, but I will release them as a kind of how that goes.